So you can see the slides, right? Okay, good. So let's continue with PN junction under bias. So previously we have discussed three different conditions, which are a thermal equilibrium, forward bias, and reverse bias. So we've also discussed what happens to the junction and what happens to the band diagram, what happens to the carrier flow in these three different conditions. So we know that when we talk about zero bias, that means a thermal equilibrium. That means we don't apply anything to the PN junction. When we apply forward bias in the second case here, so we are connecting the junction in such a way that the p-type semiconductor is connected to the positive side of the circuit, and the n side of the semiconductor is connected to the negative side of the circuit, and we call that as a forward bias. And then you apply certain voltage, and we call that as an applied bias. Okay, applied positive bias, if you like. So on the other hand, when you connect your PN junction in the reverse way, or if you connect your p side semiconductor to negative terminal and n-type semiconductor to the positive terminal, we are applying reverse bias. Okay, so when you apply forward bias, we're going to reduce the barrier height at the junction, where the effective barrier height, the recent one, is going to be given by Q times VBI over VBI minus VA for forward bias. On the other hand, if you apply reverse bias, the barrier height is going to be increased further in comparison to thermal equilibrium condition, because the recent or the latest barrier height is going to be given by QVBI plus applied bias, right? So for notation, you can either use VA for both cases to denote applied bias, or you can also use VF for forward bias and VR for reverse bias. Either one is fine as long as you are consistent in the usage of the notations. So we stop here when we discuss about the calculation of minority carrier in the opposite region. Okay, when we talk about opposite region, in this case we are talking about the concentrations of the majority carriers and minority carriers at the end of depletion region. So one is on this point and this point on the left hand side of the region at point A, and another one will be on another side of the depletion region or space charge region at point B. Okay, so these concern both majority and minority carriers of holes and electrons. For example, if you talk about applying the forward bias on the junction. So if you talk about holes, for example, then we're going to use PPA, for example, PPA at this point. Color point A, yeah? So that means concentration of holes in P-type semiconductor at point A as the majority, and then whenever the carriers, the holes travel across the junction or across the depletion region, to be more exact, then we're gonna need to know what is our concentration on the other side. And at that point, the holes that have diffused across the depletion region will be the minority carrier on this side. So since now they are minority carriers, the notation will be P and B. The carrier concentration, the concentration of holes in N-type materials at point B, right? So on the other hand, it's also true where you have to calculate the density of, or the carrier concentration of electrons, being where N and B being the majority carriers in N-type, and the moment the electrons have crossed the depletion region or the space charge region, they will be minority carriers in the P-type region, and they'll be given by NPA, concentration of electrons in P-type material at point A, right? So when you're given this sort of question to do the calculation later on, what you have to do is you have to firstly sketch this profile, the exponentially reduced profile on both sides for electrons and holes, and then label the depletion region on A side and B side. Okay, so label this A and B. So label this region. And label all the necessary points. In this case, all these 4 points. 1, 2, 3, 4. Label all these 4 points and label all the notations before you start doing any calculation or analysis. That's the very first thing to do. So when we apply the forward bias, we have discussed before that the effective barrier height will be reduced, and it's going to be given by QVBI minus VA, right? So the higher the applied bias in the forward region, the lower the barrier height will be, and we're going to have more and more concentrations of carriers crossing the junction to the opposite side. So if you look at the drift and diffusion current that we discussed before at thermal equilibrium, then we can make few assumptions. For example, we've discussed before at thermal equilibrium, there is no net carrier flow for both electrons and holes due to the reason that the Fermi level is constant. So we only have one single Fermi level at thermal equilibrium. So there is no net driving force forcing the carriers to flow across the junction. Okay, so at this point, if you look into superposition model that we discussed before, that is made of drift and diffusion component. So we're going to find that the diffusion, the drift component is equal to diffusion component for holes and for electrons as well. So in this case, the drift will be equal to diffusion, or you can also rewrite the equation as J hole equals to drift component minus diffusion component, and that is equal to 0, or the drift component is equal to the diffusion component. Okay, because they are equal but in opposite direction. Right, the superposition model can be used to calculate the total current density in the depletion region. We're going to use this one later on when we talk about applied bias at certain magnitude, and then when we need to calculate all our minority carriers on the other side of the junction. We're going to go through the calculation later on. So at forward bias using the superposition model, both drift and diffusion are large and opposing in the depletion region. So that means they are opposite in direction. So we have learned that the drift component can be approximated to be equal to the diffusion component, and therefore the drift is equal to diffusion. Drift is equal to diffusion for the holes. And this is also true for electrons, right? So you can just rewrite the equation for electrons. So Q mu E times N electric field equals to Q d E d N dx, so d dx of N, right? We have also learned about the Einstein relation, where d over mu equals to kt over q. You can also use this for electrons and hole. So electric field in the depletion region is given by this. And if you do integration of the electric field across the depletion region, we're gonna simplify the equation to be equals to this, and even simplify it to be this. Okay. So where PPA, let's look on this graph now. PP at point A, which is this, right? Or can also be approximated as PP naught, or also NA. The other side is ND. Equals to Pn naught exponential of QVBI over KT, right? This is the built-in potential. Exponential QVBI over KT, right? So this graph is also the same like what we discussed before. These 4 points need to be labeled on both edges of the depletion region. So then the PNB, if you look at PNB here, where is PNB? PNB is the minority carrier in this. So that will be given by Pn naught, right? Pn naught. So Pn naught here means the value of Pn at thermal equilibrium before we apply the bias, right? So remember last time we talked about Pn naught when we were discussing about thermal equilibrium, right? And we know that when we apply a forward bias at the depletion region or at the Pn junction, we know that the carriers will cross more and more, right? Or more and more carriers will cross the Pn junction. And as a result, when we apply the applied bias in the positive region, in the positive direction, sorry, so you're going to reduce the very high. So we're going to have more and more carriers diffusing through the junction, and we're going to end up finding more and more carriers at the end of depletion region on the other side. Okay, maksudnya kat sini, when say if at thermal equilibrium you have something like that, for example, so if you apply forward bias, you should be expecting this profile to be, okay, saya draw kat atas ni. If it was like this before at equilibrium, say this is Pn naught, then if you apply forward bias, you should be expecting the profile to be higher on the other side, okay? Because more and more carriers are now crossing the junction. So you should expect this to go up. So if you're talking about the same point, say, so that means the minority carrier concentration on the other side of the junction should also increase due to the applied bias, right? Because the barrier height is reduced. So this is what you're going to see exactly in the previous topic, in the previous page. So if you look at PNB now, when you apply the bias, so PNB being the point PN here, PNB should be somewhere here, right? At point B along this way, along this line then, is going to be given by Pn naught. So at the very same point, but at thermal equilibrium condition. So this naught, that means the value when it was in thermal equilibrium condition. PNB is the value when the VA is applied, right? So we're going to see what is the new carrier concentration at the very same point when the bias is applied, in contrast to the previous condition at thermal equilibrium, right? And that is going to be given by PNB equals to Pn naught exponential of QVBA over KT. Okay, and this Pn naught, if you look at this Pn naught, is actually given by Ni squared over Nd, right? Given by the law of mass action. Pn naught is given by Ni squared over Nd. So you just use this same component as well, exponential QVBA over KT. And the same thing is also true for NPA. NPA is for the other side, electron concentration. Maksudnya, if you look at this, if you want to plot another sketch, something like that, from the other side, coming down from N side to P side, so you're going to look at NPA. NPA. So that means, katalah this is the earlier condition in not thermal equilibrium. So you should expect the profile to be higher when the bias is applied. Okay, and that is going to be given by NP naught times exponential QVBA over KT. NP naught is the thermal equilibrium condition as well. And you can use NP naught to be equal to Ni squared over Na times exponential QVA over KT as well. So if you look at this expression and this profile, we can see that when VA is applied, okay, katalah your VA is applied, we should be expecting higher minority carrier concentration on the opposite region, right? On the opposite side of the depletion region, due to the application of the forward bias voltage, right? So the reason is simple, because the moment you apply your forward bias, your barrier height is reduced accordingly, right? The barrier height is reduced and is given by this QVBI over VA in forward bias condition. So if you increase this component, then this component will reduce, right? Therefore, your barrier height will reduce. So the border in front of the carriers is reduced already, and therefore that makes the diffusion a lot easier again. So it will induce further diffusion of carriers to the opposite region, just like the way it started when the p-n junction was combined. Okay. So the hole density on the other side of the junction, that is at the edge of the depletion region. So if you talk about the hole, then we're talking about this point, because this is the opposite of the region. If you're talking about electron, then you're talking about this point. Depends exponentially on applied voltage. Okay, so the applied voltage will affect the minority carrier concentration exponentially, right? Because you have the exponential component. So this increase of hole density in the n-type or increase of electron in the p-type is known as carrier injection, right? This is also a form of carrier injection, because when you apply the bias. So remember last time when I talked about carrier injection, it could be due to either doping or optical illumination or applied bias as well. And this is applied bias, right? So we are actually injecting minority carriers to the other side of the junction. Okay, if you're talking about p side, then you are injecting holes into n type. If you're talking about n side, then you are injecting electrons to the p type, right? So we are now injecting minority carriers. Injecting minority carriers. So why is this important? Why do you have to learn this? You're going to see later on. For example, if you talk about solar cell, so it's going to depend on minority carrier injection from optical illumination in order to generate electricity in the device. Okay, we're going to see later on in the second half of this semester after the sem break. So how does whole minority carrier density vary across the n-type region? Okay, nanti kita akan tengok. So as of now, is it okay? Is it clear that the VA will affect the minority carrier concentration on the other side exponentially? Okay, so far can follow? Paham tak? Or you don't understand certain parts of this applied bias thing? Then that's okay. Yeah. So the idea is simple. When you apply forward bias, the barrier height is reduced because QVBI minus VA is reduced due to VA increase. As a result, kalau you nak lompat pagar sekarang dah rendah, so it's a lot easier for you to jump over, to cross the fence, cross the gate, for example. So therefore, more and more of the carriers will diffuse, just like the way it started when you combine. Because the moment you see the moment you apply the bias, you will force the electrons and the holes to flow to the opposite region, right? Therefore, establishing a new value of minority carrier concentration on the other side due to the crossing of the carriers. Okay, so the minority carriers will no longer be the same as in thermal equilibrium, because in thermal equilibrium we don't apply anything. We don't apply any forward, any external agent like optical illumination or bias or whatever in order to induce the movement. It's just the natural diffusion of the carriers. But in this case, it's forced diffusion. It's no longer natural, right? The moment you combine, it was natural diffusion due to the presence of concentration gradient. But now it's like somebody pushing behind you so that you move to the front. Okay, so the somebody that's pushing is the forward bias. Right, minority carrier flow in n-type region can be shown that minority carriers in the uniformly doped space charge region flow predominantly by diffusion due to the diffusion of carriers, right? So the moment we apply the bias, then somebody push you from behind, and you're gonna cross the junction, and that is dominated by diffusion. Thus, in the n-type region, the quasi-neutral is the region outside the space charge. Piece and inside. So this is the Q and R. Okay, all right. Okay, now is the region outside depletion region to the left and also to the right. So in depletion region, the current density of the holes can be approximated to be equal to QDH dPdx, right? DDX of holes, right? So we can approximate the current to be this. So if you extend the plot just now, the sketch of the profile, so this will be the depletion region, or SCR, space charge summer. So this will be the border of the junction, if you like, right? The border. So this will be the space charge, negative, negative, the fixed immobile, fixed immobile. Okay. So now we need to know what is the next concentration of our carriers when the holes move further into the QNR region. So that means if you want to relate this, then it's going here. Going from there to there, we need to know the concentration in the QNR or quasi-neutral region. So it's like going there to there, the very same point. Okay, diffusion down concentration gradient. So the same is applicable to the end side as well. Kalau you nak plot the end side, for example, then we want to know what happens to the electrons as they move further away from the depletion region into the QNR region, quasi-neutral region, quasi-neutral region. So why this is important? We're going to see later on. When you talk about PN junction, physically, so let's now be more physical. Katalah you had a wafer. So this is a wafer. Say we start off with a P-type wafer, for example, and then then we diffuse an N-type layer on top of the wafer. On top of the wafer, I don't have the wafer here. Oh, I have the wafer. Hold on. Let me show you. Let me show you one example of our old wafer from the lab. Okay, have you seen silicon wafer before? Pernah tengok silicon wafer? Belum. Okay, saya tunjuk walaupun you tak boleh pegang, tak boleh. Let me just show you this. This is a silicon wafer. This is a 2-inch wafer from no lab. Ni dah lama dah ni. I think back in late 90s or no, early 2000. Early 2000. No lab was built back in 2005, right? So it's been 15 years at least, right? So this is the wafer from the lab. Amal penyelidikan teknologi silicon. So look at this. So it's a 2-inch, tapi it's frame already. Kat belakang ni dia orang tak contact positive and negative, something like that. So just for showcase. So it looks something like this. So this whole thing, so if you look at this diameter, is 2-inch, 5 cm. Kalau you pegang hujung ke hujung ni 5 cm. Ni pada atas ke bawah pun, that's about 5 cm. Right, so this wafer, say this one is P-type. Okay, P-type. So that means if you look at this cross section, you take dari tepi. So that's exactly what we're doing now. We are doing now. So your eyes here. So you're looking from the side. So now you're looking from the side from the camera. So dari tepi So this whole thing is P-type. Mula-mula sebelum ada N-type. So normally bila kita beli, it's a P-type or N-type or intrinsic, if you like. You can also order intrinsic, undoped. So then you can diffuse the first few hundred nanometers of the surface. Dekat surface atas, and you can diffuse a very thin layer, like 200 nanometer or so, and the whole silicon wafer thickness is like 200, 300 micron. Okay, 3 kali rambut kita, 3 times our hair thickness, and you can use 200 to 300 nanometer, right, to dope the surface to form this N-type. Okay, right. So if you zoom into this PN junction region from the side on the sketch, so depletion region yang kita ada kat sini is actually a very small region there. Okay, very small region there. So kat sini lah yang kita discuss all this stuff. Let me relate this to the drawings now. So this is your depletion region, more or less. So I'm just exaggerating here to make sure you see. It's actually very, very small. It can be just a few hundred nanometer or can be lesser than that. So this region that I'm exaggerating is actually this region. This region, okay? So kalau kat sini on the sketch dekat dekat slide ni, so that means this is your wafer. So originally this is your wafer, but flip 90 degrees. So this is the whole wafer thickness D. So this is the whole wafer thickness D. Right? Nak bayangkan wafer supaya you nampak junction tu sebenarnya kat mana. Then you just flip the wafer like that. Then you can draw this vertically. So kalau you draw this sketch, then the junction will be katalah 200 nanometers. So your depletion region will be very, very small there. Very, very small in this region. So outside this region, in the sketch, is this one will be the Q and R. Q and R. And this one to the top is another Q and R. Which region, right? So maksudnya dekat atas ni, the very small part on the surface is the QNR, followed by a small depletion region dekat atas juga. So it depends on how deep is the junction. Kalau junction tu very deep into the wafer, then your depletion region will be deeper into the wafer. But typically our PN junction is formed near the surface. It's about 200, 300 nanometer or max 1 micron. So that's where your depletion region is located. And the rest, if you imagine 200 nanometer of N-type, so that means the rest of the wafer is the whole Q and R back here. Okay, so the whole region there is back the Q and R. So my depletion region is very, very, very small. Just to relate to the concept that we're learning now, so that you know where exactly all this stuff in the wafer. Okay, so sekarang nampak tak wafer tu macam mana, junction tu kat mana, depletion region tu duduk mana, Q&R tu kat mana, on this wafer. Can you translate all this sketch into this now? That's the most important thing. Because what we're learning now is the physics, the fundamental, the sketch inside. But the actual thing is this, in this wafer, at the surface, at the back, and stuff like that. But can you see that now? At least. Right? So that's the most important. When you see wafer, that's what you should be able to imagine. Right? Physics ni imagination kan. So apa yang kita belajar ni is mainly imagination first before you see the actual thing. Right? So whatever you learn in the theory, you should be able to relate to the outside world. Because especially if you talk about this course, I briefed you in the first day last time, during the first day of the class. This course is going to connect the physics to the outside world, right? The physics is what you learn on this page, and the outside world is this, right? So this is the actual wafer, 2-inch, and then this 2-inch is going to be cut into small dies, small pieces, and it goes into your phone, it goes into your whatever laptop, whatever like gadget you order. Okay, chips in the IC, chips in the whatever card that you have, right? So the complexity of the device depends on the purpose, right? So if we talk about solar cell, then it's not that complicated. It's just a simple PN junction. When the light strikes the surface, you're going to have electricity out of it, right? Going out through the outer circuit. If you talk about integrated circuit, then it's going to be more complicated. If you talk about MEMS, then less complicated. If you talk about chips for parking, for example, parking kereta, then it's just a very simple palang up and down and stuff like that. So it depends on the complexity depends on the function, right? Then if you talk about these chips in the phone, then it's going to be, of course, complicated because your phones now can do so many stuff, right? So yeah, I want you to be able to relate that. I'm just going to stop here first. So we're going to look into the calculation tomorrow. Tomorrow's what? Today is Thursday, right? Tomorrow's Friday, no class. So next week then. So next week we're going to continue with, oh next week cuti kan, alamak saya lupa lah next week cuti raya dah. So anyway, tak apalah, kita continue lepas raya. We're going to look into this. Okay. So we're going to look into how do we actually calculate the concentration down this. Okay. Tadi kita dah tengok the calculation within the depletion region, SCR. So kita dah tengok point yang 4 point kan, PN not, PNB and everything. So if you want to draw this again, then it's going to be something like that. Okay. For p-type, for holes. Next, we're going to see what happens to the carrier concentration if you move into Q and R. And then also to the left, right? Somewhere you got to the left one, somewhere we're going to see what happens next into Q and R. So the question you ask, reverse bias. Yes, ada device yang pakai reverse bias. We're going to see later on. Okay. Ada device yang based on reverse bias. Most that we know is based on forward bias, tapi ada yang pakai reverse bias. We're going to see, I think, at the end of this, or this one, Zener effect. We're going to see the Zener effect later on about reverse bias. So we're going to see what happens when we apply so much reverse bias. So for example, this I just preamp lah. Two physical mechanisms give rise to reverse bias breakdown in PN junction and all this stuff. We're going to learn about reverse bias condition after we finish the calculation on the forward bias. So after the SEM break, we're going to do this estimation or approximation in the Q&R of both sides. And then you're going to see the profile like this. And then kita akan tengok, we're going to see what happens if the diode is thin versus when the diode is thick. Okay, maksudnya if your PN junction is a very thick one, for example, in the wafer, then what is going to happen? And on the other hand, if the wafer is very, very thin, or you don't use wafer, for example, 200 micron, but what if you use thin film, right? Wafer 200 micron. What if you use 1 micron, but then you slice the wafer like 200 times and you pick only one slice of salami, daripada sini you ambil satu slice of say 1 micron of 500 nanometer and form PN junction in that 1 micron slice. So what is going to happen? Well, we call that as a thin diode, right? We're going to learn about thick diode concept and also thin diode, right? Apa yang akan jadi bila thick, apa akan jadi bila thin. So because these two conditions, thick or thin, are going to determine the performance of our semiconductor device later on. For example, if you talk about solar cell, kalau you tengok solar panel yang we have on the roof, then they are based on all the thick diodes, right? Because they are based on wafers, 180 micron in manufacturing. Okay, so that's about this thickness, more or less. But we also have some other technologies of the solar cell which are based on thin diode, like a few hundreds of nanometer or even less than that, in order to generate the same amount of electricity out of the device. So in that case, we need to know both thick diode concept and also thin diode concept, and we have to know the fundamentals of both cases in order to understand the operation of our devices, which are based on either thick or thin diode later on. Okay, so that's all for today. Any questions? Any other question? So we're going to move into Q&R after the SEM break. Okay, ada soalan lain? So all good so far. So to date, we have finished discussing the carrier concentration concept or the calculation equation in the SCR, in the depletion region. So next, we're going to go outside of the depletion region to Q&R of N-type, Q&R of P-type. We're going to see how does the thick and thin diode affect the profile. Right? That will determine the performance of our semiconductor devices later on in the second half of this semester. So tak ada? Right then, kalau tak ada apa-apa, Yeah, we're done for this week. So enjoy your break. Stay safe. Dan selamat Hari Raya lah. Selamat Hari Raya. Walaupun belum Raya lagi, saya ucap siap. Sebab kita dah tak jumpa hingga selepas Raya kan. So we're gonna come back the week after Raya. Right? Okay, bye-bye. Take care. Assalamualaikum. Selamat puasa dan selamat Hari Raya.
Selamat Raya juga.
Right. So yang nak balik tu, you gonna start you're going back to hometown tomorrow kan? Betul?
Betul, Doktor.
Okay lah, selamat pulang ke kampung ha. So kalau you drive, hati-hati memandu. Right, hope everything is okay, everything is smooth. Doakan COVID ni goes away as fast as possible so that we can go back to normal. Okay, bye-bye. Take care. Assalamualaikum.